confirmation seminar. So RIPON's project is about improve the performance and stability of perovskite solar cell through material engineering. So in the past 1 year, so he has worked on different components in the device and trying to understand the mechanism and also to improve device performance. So to be honest, to work on a device is very hard, it's very challenging because even if one component is not right, so the whole device won't work. So, and I leave it to Ripon to show the details about his work. So, and also I leave it to you for the comments. And also I'm sure all your comments will be useful and help for him to improve. So in the next stage. Okay, so Ripon, please.
Thank you very much, Professor Hong, and good afternoon, everyone, and good afternoon, review panel members. And today I'm going to present my candidature report on enhance the performance and stability of perovskite solar cell through material engineering. Before I explain all my works, I'll just go through some which I included in my presentation. Is introduction and background of perovskite solar cell, research directions, proposed methodology, and process progress to date until last 1 year, what I have done, and conclusion with the future works which will be done next 2 years, and some acknowledgement. So at the beginning, what is perovskite solar cell? Perovskite solar cell is third generation solar cell. This is mainly similar to the other solar cell like dye-sensitized solar cell or silicon-based solar cell. But this one is a little bit different because of its name, the perovskite. The perovskite solar cell actually is named from its structure, absorbent structure. That is the perovskite structure. So because of this name, the perovskite, this solar cell name as perovskite solar cell, and the perovskite structure contains the methyl aluminum group at the middle, and the halide group will be in the outside of the things. And the structure of the perovskite solar cell is quite similar to the dye-sensitized solar cell, which contain the one substrate and one metal contact. And between these two, there is a light absorber layer. There is perovskite layers, and this one sandwiched with the mesoporous layer and cold transport layers. So this is the typical perovskite layer in device. Right, still now there are two different types of perovskite devices. One is mesoporous devices, another is planar device. So the mesoporous perovskite is when we are using metal oxide mesoporous layer on it, there is no mesoporous layer. And if we don't use any mesoporous or any scaffold, just only end contact, then this is known as planar device. And there is another NRP junction device that is actually created because sometimes we use different type of whole transport materials which is not favorable for deposit on perovskite films. That's why scientists propose another one to deposit the whole transport layer on the conductive layer, then deposit the perovskite material on it. So this one can give a different structure which is known as inverse structure device. Then why perovskite solar cell? Perovskite solar cell, actually the solar cell technology, the research is going on last 100 years, centuries, and there's a lot of development with the silicon-based solar cells. Besides that, still there are a lot of problems with the silicon-based because of the fabrication process and also the high cost. You want to get very high efficiency silicon-based solar cell for commercial use. Then the perovskite solar cell actually comes up in 2012. This is not very old device where when the first group reported is 9% perovskite device. Then after 2015, end of 2015, it's rise to 21%. So 2012 to 2015, within few years, it's rise from 10% to 21%. So it's almost like 2 times. This is really very promising research field. So besides this one, because perovskite solar cell is cheap material used and manufacturing cost is quite low. So if we compare with these things with the other solar cell, then this is benefited. And then second one is easy to fabricate compared to other silicon-based solar cell or other cells, and this one has very high performance. So these 3 main parameters, I should say, is make the perovskite solar cell most important and for the researcher nowadays. Besides this, there are some few feedbacks. This one is the stability problem for the device, then reproducibility for high efficient device, And toxic materials, mainly the lead source, which one is used in the perovskite, is quite heavy metal and toxic. So people are trying to replace the lead source and can get toxicity free. But if we compare the device performance, the quantity of lead is used in the perovskite solar cell, then it's not really too much. If we can develop any other capping technology, then maybe we can, sealing technology, we can maybe prevent these things. And the last one is expensive whole transport materials. Till now, people are using organic whole transport materials, which is quite expensive. So these cost of whole transport materials actually increase the price of overall perovskite device cost. Then the working principle of solar cell. So working principle of solar cell is quite similar to the dye-sensitive solar cell. So here is the first image for the cross section. This is just a small animation showing how the electron is passing through. But here there is a schematic diagram and just simply explain how it works. So when light strikes the perovskite solar cell, so the electron transfer from the valence band to the conduction band, then it transfer to the charge transfer carrier, then it will go to the conductive metal like IT or FT, and then total circuit will complete and metal will release electrons, spiral will give these things. But beside these things, for perovskite solar cell, it is interesting that like the electron will jump from perovskite to TiO2, or spiral will go from here to perovskite. Which one will done first? Still, there are a lot of debates on it. So researchers are working on it, which process actually done first. Besides this, there are some few drawbacks. One is, however, if the device is working fine, but if there is a pinhole, if there is a device film is not tuned, then there are some problems with leakage. So it can happen the electron will transfer from perovskite to spiral, or maybe from perovskite upper layer to conduction band to valence band, or TiO to spiral, or from TiO to perovskite. So this kind of drawback or recombination can happen due to the leakage, or if the film is not very uniform. Then to understand the perovskite device, not only perovskite, solar cell device performance, we just use some calculation to define their performance. So the efficiency is calculated from the power we get from the device and the power we give. So basically the power of the device mainly depend on three main parameters. It's short circuit current density, open circuit voltage, and film factor. So short circuit current density and voltage is also depend on the materials which one we are using. But the film factor is mainly depend on the, from the image you can see that the film factor can be calculated from the DMP and IMP. So this is also important. Film factor is also proportional to the shunt resistance and series resistance. So these two parameters, series and shunt resistance, the resistance is also the properties of perovskite device different layer. So if we can control and optimum the device layer, then we can optimize the series and shunt resistance, and only then we can get high efficient device. So from the literature, there are like a lot of works on perovskite materials. Mainly methyl ammonium lead halide groups are used for the perovskite solar cell. So there are like iodine, chlorine, or mixed with iodine and chloride or bromide. Those materials are mainly popular for the perovskite device fabrications. And I just also listed the band gap. So the band gap of perovskite materials is also very important for high efficient device. And people are also, recently there is a paper published on ferromedium lead iodide mixed with other methyl ammonium lead iodide and chloride, and get very high efficient 20.1% of device performance. That is really very high device performance. And the JSC is 24.7, which is quite close to the theoretical JSC, short circuit current density. And so if we can just keep other parameters, and if we can make a very uniform device with long-term stability, then this one can easily replace the silicon-based solar cell in future. So beside the methyl ammonium group, they are also used cesium, and people also try to replace the lead with tin. So to understand the different materials used for the perovskite, this is actually lie behind their morphologies. So if we use the lead iodide, we can see some films is not really very smooth, it's quite rough. And if we use the chlorine, then we can get very smooth flames. There is not that much of roughness and no pinholes. And this one is for the chlorine and iodine. So if people like to get a smooth pinhole-less flames to get high performance device. And when they use the bromine, this is very interesting. This one can get a very high grain size compared to other fluid. But bromine has a high band gap, which actually helps us. People like to use bromine in the perovskite to get high VOC, voltage, open circuit voltage. So this one, they thought if we can increase the voltage, if we can keep the current density and field factor, then we can get very high efficient device in the future. So that's why they like to use bromide. But when they use homomedium lead halide with the meat, they found very smooth and pinhole-less flames. This is maybe one of the main reasons to get very high efficient device, which is compared to the tin iodide. You can see is very rough and there is a lot of pinholes. So this is one of the reasons might be for getting very low performance from the tin. So the same with the cesium. The cesium is also uniform, but it's not smooth like other films. So the smoothness and pinhole-less films is important to get a very high efficient device. Then I checked different mesoporous layers. So in the literature, they use zinc, vanadium oxide, cerium, aluminum, and zirconium. Aluminum and zirconium, those two are not used as a scaffold, insulating layer. And Henry Snell found that like when they use the aluminum oxide, they can get very high VOC. Well, that's the initial state, but afterwards they got about 1.1 volts of VOC when they use aluminum oxide. So aluminum oxide is also one of the promising materials for the mesoporous layer. But mostly in the perovskite solar cell, people use TiO2 mesoporous layer because it has been using since for dye-sensitized solar cell and other solar cells. So we are also interested with the TiO2 mesoporous layer. So I found from the literature there are like different, they use different thickness for different papers and different research groups, but there is not that kind of connection, why we need to use 100 nanometer or why we need to use 600 nanometers. So this is actually depend on what kind of perovskite material we are using, because different perovskite materials has different diffusion length, and depending on the diffusion length, they like to use different thickness. But if we want to use an optimum thickness for optimal perovskite materials, then we have to tune the mesoporous layer thickness. Then the last one is I also checked the blocking layer effect. So recently, last month, there is one paper published on nickel manganese lithium oxide. They used pyrolysis and got really very high field factor, 82.7%. This is really very high field factor, and the performance is also quite promising. But beside this one, they also use neodymium oxide or fluorine or cesium carbonate or zinc oxide. So depending on the mesoporous layer, people usually like to use TiO2 if we use TiO2 mesoporous layer. So that's why I also focus on TiO2 mesoporous, TiO2 blocking layer. And there are like few techniques. They use spin coating, soldier method, electrodeposition, thermal oxidation method, and spray pyrolysis method. So the last one, spray pyrolysis method, is easy method and can make a very smooth pinhole-less flames, and that till now giving us a very high efficiency. That's why I also like to, I'm interested with the spray pyrolysis method to make my blocking layer. Then the research gap and objectives from the literature review, I found like the tuning the TiO2 blocking layers and charge transfer layers is, they have done like few papers, but there is no close linking with all the papers. They said they use 50 nanometers of blocking layer or maybe 150 nanometers of mesoporous layer. But there is no trend like why we need to use that, why we didn't tune these things. So that's why I think this is one of the research gap. Then the optimizing perovskite film deposition. Research group had done different perovskite materials for different morphologies. So this is also one of the important points. Then high efficient device requires reproducibility and long-term stability. So most of the device recorded, okay, they got high efficiency, but very less papers showing that the reproducibility. If they show the reproducibility or long-term stability, then the device performance is quite low. So this is one of the gap for the research. So if you want to understand the long-term stability, then we have to understand the degradation mechanism of perovskite. So this is one of the, and there is not so many papers has, research work has done for the degradation mechanism. So this is one of another parameters. And finally, as I said, the whole transport materials organic is quite expensive. So this is one of the points where people are trying to change this one to get a new whole transport materials to minimize the cost, either using hydrophobic or doping, so that we can make the device more long-term usable. Then the expected outcomes. So from the literature review, I found like if we can make a very good, nice TiO2 compact layer with no pinholes, it can improve the open circuit voltage as well as the field factor. And I say these two parameters are also important for the high efficient device. Then if we can optimize the TiO2 mesoporous layer, this one might be help us to transfer the electron faster and also can give us reproducibility properties. Then I also checked that if we can find a suitable method to deposit the perovskite film, then we can also able to find a uniform surface with no pinholes, which can improve the crystallinity and also better device performance. And finally, optimize the whole transport layer can make a uniform film thickness, which can improve the VOC and overall device performance. The methodology used in the literature is mainly sequential deposition and the vapor deposition. Sequential deposition is solution-based depositions, and vapor-based is quite complicated deposition method. So for the sequential deposition method, this one is two types. One is two-step method and another is one-step method. For two-step method, from the we usually deposit the perovskite layer on the top of mesoporous layer here. So this one is easy to control the morphology and interface. Reproducibility is quite high, and also this one doesn't rely on the diffusion length, doesn't rely on perovskite materials because we are using the mesoporous layer, so we don't need to think about the diffusion length for the perovskite materials. So this is the actually advantage for the two-step method. And there are some few drawbacks, like this one require longer time than other methods, and lead remain in the surface, which makes the degradation process or long-term stability. And mainly whenever we want to use the mesoporous scaffold, this one requires complex structure and fabrication process. Then there are people propose one-step method. This one can give a very nice flame morphology, and also this one have fast crystallization process properties, excellent coverage, and energy saving process. But this one have few drawbacks. One is the solution-based, this one, and not suitable for all kind of lead, because if we cannot dissolve the lead properly in a solvent, then it will case we will not able to get a nice flame. So this is also important for the fabrications. Then the vapor deposition is a mechanical process. This one is it requires high cost and require complex setup, but this one can give us a very uniform flames and with less pinholes. But the problem is it costs high. So based on this literature, I felt like if I can use two-step or one-step and find out which method is suitable for my work, that's why I just use both of these methods here. So for device fabrications, as I said, I use sequential deposition method. So first I use two-step method, prepare the TiO2 compact layer with the spray pyrolysis, then deposited the TiO2 mesoporous by spin cooling method, and at 500 degree temperature, prepare the lead iodide solution, and then deposit it on the mesoporous layer. So here is I put some, why I said that it is important to lead halide soluble in the solvent. If it's not soluble in the solvent, then we will get rough, and it will cause rough perovskite layer, which is bad for the device performance. Then one-step method doesn't require two-step and long process. It's just we mix the methyl ammonium iodide with lead halide salt and then deposit it in the flames on the TiO2 blocking layer, and it easily can. It is very fast crystallization. We can easily get the perovskite layer whenever we finish the spin coatings. Then we another samples at 85 to 105 degree temperature, depending on which method we are using. Then the last one is we deposit the whole transport materials on it, then clean the surface, deposit the gold, and the device is ready to measure. So to measure the device, we use solar simulator, electrochemical impedance spectroscopy, and IPC to measure the device properties. And we use the ASEM and AFM to find the device surface morphology and topology. We use UV spectroscopy and ellipsometers to understand the reflections and absorption properties of the flames. And we use XRD photoluminescence, and I didn't actually put here NMR and other analysis, DSSC and others analysis I have used to analyze my flames and materials throughout my last 1 year's project. So at the beginning, when I prepare my MAI in the laboratory, so I need to check the properties of the MAI, and as this is MAI is organic, so we don't have that much of database to compare with the XRD patterns. So I just compare with the reference, and I found like this one have quite similar peaks. So there is no problem with that things. But there is, I put like 2 times purification and 1 time purifications. This is why I put, because methyl ammonium iodide is hydrophilic, so it can absorb water. And if methyl ammonium iodide absorb moisture, then this is not good for the device fabrications. So that's why we have to make sure that the MAI doesn't have any moisture content in it. So if we want to do that, we use NMR, proton analysis. And from the proton analysis, this is the one step, one time, and this is the 2 times for the NMR analysis. This 2.38 represent the methyl group, and this one is ammonium group proton, and this 3.34 is for the water contained proton. So from here we can find, if you use a one time, then it's 8.39 ppm. When I did 2 times, it reduced almost 10 times to 0.03. This is just a comparative data, but it's not showing that like if you do 2 times, it can make a very nice uniform moisture-free MAI. This is very important for device fabrications. Then after that, I prepare the device with the 2-step method. So I use the TiO2 mesoporous layer, which is commercially available with the 20 nanometers and the lead iodide solution and deposit it. This is real crystalline, and you can see this is about like 200 nanometers length and with 100 nanometers of dye. This is very uniform films. But when we deposit the perovskite layer on it, we can see a lot of pinholes, a lot of holes here. We can easily see the mesoporous layer. So this is one of the problem for 2-step method. And I did the XRD to investigate the perovskite layers. And from the cross section, you can see the direction of perovskite, and the direction from the XRD is quite similar. It's 110 direction. So this is quite existence with the cross section and also the XRD patterns. And another point is like I also checked the lead iodide content in the films, and we found like this one has a lot of lead iodide remain in the films. The steric also show the lead iodide content in the films. So this is also one of the problem for the 2-step method. So if you want to react the whole MAI, we need longer time. If we do longer time deposition, it can degrade the perovskite. So this is also a problem for 2-step method. And from the XRD patterns, when we check the peak like 110, 211, and 220, we compare with the reference, and we found that our perovskite is cubic structure from the reference. So after I prepare the device, I found like there are a few proceedings we have to follow before we prepare the device. The first is we have to heat the FTO after cleaning that ones to remove the organic compound. So this one actually requires longer time, and I felt this one can increase maybe the resistance of the device. That's why I prepare device without heating and with heating. So this is just the cleaning process. So I checked this one, and I found like if I don't heat the sample after I clean it, then the resistance, series and shunt resistance is quite promising than if I heat it. So I didn't actually did a lot of investigation on it, but as I mentioned before, the series and shunt resistance is one of the key parameters for high efficient device. That's why I think if I don't do a heating process while I prepare the device, it can save my time, save energy, and I can prepare the device with high efficiency. Then I also checked the time, wanted to minimize the time for the TiO2 mesoporous layer annealing process. So I used 2 different. One is just anneal the TiO2 mesoporous layer at 500 degree temperature. Then I just take it out the samples and cool it within like few hours. And another is just I keep it overnight to cool it at the normal temperature. So I found if I take out the samples very after the annealing process, then there is a lot of porosity in the process. The porosity of the film is quite higher than if I do it in a normal natural cooling process. So this is one thing I found from the quick cooling and natural cooling process. And then when I make the device, I found there is a huge difference with the device performance. So when we use the natural cooling, this one gave about high performance compared to quick cooling. So the performance is just to compare with without quick cooling and natural cooling process. It's not like very high efficiency. Then I checked the device like 6 days and checked the device stability. And I found that like first 2 days the device performance is quite high, then it dropped, but it started to rise after 4 days, and it's rise to the maximum of like about 3% of efficiency. So my device, if we use the mesoporous layer, this one can last about 5 to 6 days. I actually need to do a long-term stability test to finalize these things. This is the initial work I have done. Then I also say the literature said that people use 4200 or 80 nanometers of TiO2 compact layers, but no one said like which compact layer is better for the device performance. So I did the systematic analysis with different compact layer thickness. So I started with the 18 nanometers till 150, which is controlled with the spray times in my whole process. And I found like 3 times give me 18 nanometers of thickness and 150 from the 9 times. I also checked the AFM topology, and I found like if we increase the spray time, this one also decrease the roughness of the films, which is also quite similar to the result I got here with the thickness. Then I prepare the device with different spray time, and this is 3, 5, 7, and 9 times of device prepared from the spray paralysis. And here you can see that like when the thickness, when the spray time is 3 times, there is a difference in the current. So this is because the hysteresis. And but when this is 5 times, the hysteresis become less, and when it is 7 times, the hysteresis become more less. This is very normal phenomena for the perovskite solar cell, the hysteresis. But we found like this is also depend on the thickness of TiO2 compact layer from my experiment. And when the compact layer is quite high, the hysteresis is become very high. However, from my experiment, I found that when I use 5 times of spray paralysis, I got the highest performance is 5.63 performance. But you can easily see that 5.63 and 4.3, they are quite close. So 3 times and 5 times are quite close. But you can just also plotted the voltage with the different spray time, and I found that the voltage didn't change a lot. But when I plotted the fill factor with the spray time, I found the spray time actually changed, the fill factor changed from 80 to 40%. So it's almost half of the fill factor with the spin coating, with the spray time. So this is also interesting, like when I use 3 times, I got the highest fill factor is 83.7%. So the best efficient device, last time I said neodymium manganese we used, they got 82% of fill factor. But when I use 3 times of spray paralysis, I got 83.7%. So this is quite higher fill factor than other literature. So I felt like maybe 3 and 5 times between these two is the best compact layer for me. Then I just focus on the mesoporous layer thickness. Then because literature said they use usually 350 or 375 nanometer of mesoporous layer for fabricate the device. Then when some paper they said if they use 150 nanometers of mesoporous layer, then it can give a very high performance. Then that's why I just tuned the thickness of TiO2 mesoporous layer from 570 to 170 nanometers. Then I use those mesoporous layer to fabricate the device, and finally I found that, so this is the initial device parameters. I use 150 nanometer blocking layers and about 350 nanometers of mesoporous layer, and the perovskite layer is 250 and 150 for the spiral layer. And the same things is like here the spiral and perovskite is almost the same, but the mesoporous layer is 160 nanometers, around 150, and the blocking layer is about 60 nanometers. So when I tune those things, I got about 10.39% of efficiency from the 5.2. So this is showing that after I optimize the blocking layer, optimize the mesoporous layer, I got the device performance about 2 times, 2 folds. So this is not end of the experiment, because you can see for the 10 times device, the whole transfer layer is not very uniform, and the perovskite layer is also not very uniform. But from this here, from the ACM cross section, you can find some capping layer on it, so which actually prevent the leakage of whole transport materials penetrated to the mesoporous or compact layer, and gave us a high performance device compared to the just only previous device we have prepared. Then after I prepare the device, then I try to check the device reproducibility because that one gave about 10.5% efficiency. So I check the device and I make about like 20 devices and check their properties. So and I check the voltage didn't actually change too much. So it's about 0.95 to 1.1 volt remain for all the devices. And the current density is also remain all time about the constant 13 milliampere per centimeter square. Then I also check the efficiency. So the efficiency also didn't drop for all the device. So these actually parameters can say that the device reproducibility for my experiment is quite fine, and I can say, okay, the device reproducibility is very good. Then, because I said like I optimize the device compact layer, then this is not only saying that okay, this device gives us a very high performance. So that's why I just use that 3 times compact layer and make dye-sensitized solar cell to check the voltage decay. Because if we can check the voltage decay, then we can say okay, the films is quite uniform, no pinholes, and that's why we got very high performance. And from the voltage decay, we saw that after we close the light, the voltage decay didn't actually finish until 120 seconds. I mean, until 2 minutes, the voltage didn't reach to 0. So this one actually reveals that my compact layer is really very nice and there is no pinholes. I also checked the UV spectroscopy for my device, and I found that the absorption is about 750 to 350 because we cannot see there is some problem with those. We cannot measure these things, so I just keep it 400 nanometers. So this one actually showing that like the absorption properties of the metal aluminum lead halide is really very good. That's why we also got very high performance. Then, after I work with the 2-step method, then I wanted to use the 1-step method because my previous slide I showed that like this one there are a lot of lead iodide remain in the flames, and the flame surface is not uniform. But if we use 1-step method, then the flames is quite uniform. That's why I started to work with the 1-step using 1-step method. So for the 1-step method, what I say, this is the very beginning when I prepare the device. So 1-step method, this one is use lead halide mixed with iodine and chlorine. And I found that like if we mix these two, and 1-step method can give us almost very uniform flames compared to 2-step method, because 2-step has a lot of holes here. Well, this one has there is holes, but as I said, this is the very beginning work. So I just wanted to make 1-step method to prepare the device. Then day by day I tune the flames and other parameters to get a very uniform device, which I will show you in my last slides. So when I prepare the 1-step flame, perovskite flame, I checked the XRD, and I found for 1-step method there is no lead iodide or lead chloride remain in the flames if I compare with the 2-step. So this is one of the findings, like if we use 1-step, there is no lead remain in the surface. So this is one I got from the my device 1-step method. Then I use what I said for the 2-step method. The 3 times and 5 times are quite close. That's why I use these 2 parameters to make planar structure with 1-step method with the 3 times and 5 times. And here where I said before, like 3 times has a little bit higher hysteresis we saw previously, but 5 times has less. This is also the same properties you can see for the planar structure. However, because when we have tuned the compact layer, it's 3 times, it's about like 70 nanometers. We found that the 3 times for the planar structure give us a very high efficiency, about 7.93 compared to 5 times is 5.43. Well, this is the initial works, and that's why I said the film from the cross section you can see the film are not really very uniform, even though whole transport layer is also not uniform. So this is one of the problems for device to have low efficiency. So I said like I should mention like the film is not uniform. That's why this is one of the reasons we have low efficiency. And this is initial work. So I started to tune the film thickness and whole transport thickness with my other experimental conditions. After I got high, relatively high efficiency in the Perovskite planar structure. Then I wanted to use, I wanted to check the reproducibility for the one-step method. So I put here the 3 times spray devices, and we can see the device voltage didn't decrease too much. But the interesting part is if we use one-step method, the device voltage is quite low. It's about 0.8 volt to 0.7 volt to 0.8 volt. So this is quite low. But the current density is remain always constant, is 15 to 16 milliampere per centimeter square. Well, compared to the high efficient device, the current density is also low. But the film factor, I found that for 3 times is quite similar, or always about 60% of film factor. And the efficiency, if I see, then all of my devices showing the efficiency 6.5 to 7.5. So it means that the device reproducibility for the one-step method is also quite similar to the two-step method. Then after that, I also wanted to prepare something different, and I got some iron oxide. Iron oxide is mainly used for the water splitting properties, and not only, I mean, no one used this one for the solar cell because of its insulating properties. So, but I found like a Henry Group, they use aluminum oxide as a scaffold materials, and they found like this one give a very promising data, efficiency 10.9%. So this is actually influenced me to prepare, use iron oxide as a scaffold materials, because no one actually used this one. So for that one, I just use different thickness of iron oxide, which is like spin coating methods to check the device performance. Why I wanted to use iron oxide? As I said, this one is mainly used for the water splitting, and no one used for the solar cell or disintegrator or Perovskite, no one. So that's why I thought maybe it can be usable. The another point for using the iron oxide is the morphology. This is cubic structure. So the iron oxide is cubic structure. The Perovskite is also cubic structure. That's why it makes me interesting. If we can combine this similar morphology, maybe it can help me to get high efficiency. And for the also from the XRD patterns, we found that this is very nice materials. So that's why I actually like to use that one. So when I prepare device with a one-step method, I found the device actually didn't work as my expectations. And you can see there is a huge hysteresis for the 3, 5, 7, or 9 times coating layer. Then I also compare it with the mesoporous layer. So I put mesoporous layer, and I also put the iron oxide. And from the data, I found like mesoporous layer gave me about 9.68, but the iron oxide gave only 1.93. This is really, really very low. But as I said, the morphology and the other things are quite promising. That's why I thought maybe if there is something I missed, so maybe if I can tune the things, maybe in the future can be iron oxide can be used in a scaffold layer. And here I also show that like different thickness of iron oxide, showing the relation between the voltage and film factor. And we found like if the thickness is about 7 times, then the film factor and the voltage is quite high. So this is also interesting. That's why I say maybe we have to tune some other parameters. Maybe in the future you can get high efficiency from the iron oxide. So this is the cross section of iron oxide, and this is after developing the Perovskite layers and whole transport layers and other properties. I have tuned those things with other students, and then when I make the device, you will see very nice uniform flames of whole transport and also the Perovskite layer as well as iron. So this is very interesting because the whole transport layer is quite uniform. Perovskite layer is also uniform. Everything is uniform, but why the iron oxide didn't give a very high performance? So that's why I did the photoluminescence decay, and from the photoluminescence decay we found that like when I used methyl aluminum lead iodide, so this one the time is about 20 nanoseconds, but when I mix that things with the cubic iron oxide, the decay time is 58 nanoseconds. So from this decay we can find like that whenever we introduce the iron oxide in the Perovskite materials, the lifetimes increase too much. So this is one of the problem to have low performance from the iron oxide. And I also check the balance position of the iron oxide. So the iron oxide position is behind, between the TiO2 materials. So because we are using also TiO2 materials for the blocking layer. So this one should work, but what I say, maybe there are some few parameters, few points missed. That's why we cannot actually tune to get high efficiency. Maybe in the future, I will try to use this one and get a high performance. Then, as I said, like throughout my research, I was trying to tune the film thickness, like the whole transport layer, Perovskite layers, and other layers. But there are a few students came from Germany, and we started a collaboration work, and then we actually tuned the Perovskite layers and also the whole transport layers. And like last 1 month ago, last year after the Christmas, we got about the device performance is 15.6%. That is highest device performance ever from our group. And the data is actually we are working on these things, and we are going to publish the paper in near future. That's why I didn't actually put all the data and other parameters here. But this is the works I have done last 1 year. Yeah, so I can make the conclusions like for my last 1 year's works is like I found like if I don't use heat treatment, this one can give me high device performance, so I can minimize the time. And also I found like if I use 5 times spray, this one can give me very thin hole-less TiO2 compact layer, which gave me 5.63 at the beginning. Then I actually tuned the mesoporous layer and to 150 nanometers. Then when I use the optimum TiO2 blocking layer and TiO2 mesoporous layer, I get the device performance 10.4, which is 2 times than the initial device performance of 5.2%. And I used the cubic iron oxide and got the highest performance is 1.9, is almost like 2% from the one-step method. So this one is maybe in the future can try to get high efficiency. And from the PL measurement and entire lifetime of the scaffold iron oxide layer, then the Perovskite layer suggesting then unfavorable charge transfer properties of this is maybe one of the reasons we found not to have high efficient device. And finally, using optimum TiO2 compact layer, pinhole-less Perovskite layer, and a whole transport layer, we achieved the highest device performance of about around 60% of device performance. So based on my 1 year works and my understanding on Perovskite solar cell, there are a lot of parameters actually still need to tune to get high reproducible and high performance device, Perovskite device. So that's why I'm just also interested to use different environmental conditions to deposit the TiO2 compact layer using the spray pyrolysis, because no one actually done this kind of thing, so there is no systematic analysis or research on it. So this is one of my priority work for the future. And another is, as I said, like the mesoporous layer mixed with the carbon materials and others gave very promising result recently. One group actually showed, and I also use carbon and mesoporous layer together TiO2, and I got very stable device like along with 5 or 6 days. Actually, I didn't put the data here. So, and another is like tune the whole transport materials through dropping on incorporating carbon materials and without organic materials. This is also one of my key research with the next 2 years. And finally, I would like to use a new P-type inorganic whole transport layer for the stable, because I already got high efficient device. So if I now implement a new whole transport materials, then if I can keep other parameters, then it will be easy for me to get high efficient device in the future with the new whole transport materials. So finally, I would like to thanks to my principal supervisor, Hong, because she gave me a lot of suggestions and throughout my last 1 year, and really suggestion to get the high efficient device. Also John Bell to be my associate. And also I like to thanks to CAP technical staff, because for my last 1 year they gave enormous help for me to get this high efficiency. I also like to thanks to my group members, Dan, Howard, Tanfei, Vincent, and others I didn't mention here. And the collaborator here, we are just working with the Germany University of Cologne, Chenol, Zhong, and Pyong. They did a lot of work last 6 months, and they almost finished their work here, but we really got a very high efficient device. So we will continue the collaboration with them. And finally, the collaboration with the UQ Melton, he also helped me a lot during my last 1 year presentation. So that's all from me today.
you go to slide 21,
Okay.
it may just be an optical artifact. Slide 21.
This one?
Oh yeah, that one.
Yeah.
The green curve there,
Mm.
that almost looks like you've actually got increasing current with increasing voltage.
Yeah,
Yeah.
right. Because this is reverse current, so it's 1.04 volt. This is quite high voltage
Yeah.
compared to other parameters, and that's why we got like the fill factor.
No, sorry, just that top section looks like you've actually,
This one?
yeah, no, on the green curve.
Okay.
That point just there where the pointer is actually
Uh-huh.
to be a higher current than the short circuit current.
Okay.
Is
So,
that-
okay, so that is why we got like a high fill factor, because fill factor is also depend on the highest JSC
Yeah.
and VOC. But this phenomena is like, because if I use the, if you see like the others device, so these are almost for the similar. So actually, maybe why it happened, I've not.
It's unusual to see.
Yeah, it should be a small line.
Yeah.
When you build a device, what whole transport materials you use?
Spiral.
Spiral.
Yeah.
Yeah. And it seems the whole transport materials is very important.
Yeah.
I didn't remember tables. And when you work on different
Well, that is actually my project to work with new whole transport materials. But when I start the Perovskite device here in the QT, before I work with the dye-sensitive solar cell, so I know there are a lot of parameters actually affected the device performance. So that's why first 1 year I wanted to understand different parameters which affect the device performance. Then when I'm very much familiar with which parameters actually give me low performance or high performance, if I know that things, then if I implement the new materials, then it will be like, okay, standard device, I use new, then it will be more.
Yeah, so your current work mainly focus on to modify the compact layer.
Yeah. So I actually work with the compact layer, also work with the mesoporous layer. Then when I go to one step method, I tune the Perovskite layer uniformity.
Yeah. When you choose the compact layer materials, what thing do you think is most important?
For the compact layer, the first thing, the film should be not too much thick, and there should not be any pinhole. Because if there is any pinhole, then if somehow there is a channel through the whole transport and Perovskite to the conductive class, I mean FTO, then it will be short circuit and the device performance will be very low. And if the thickness of the compact layer is quite high, then we will not able to get very high performance. So this is actually also because from here you can see like 3, 4, 5, 7 times. So this one is showing the trend.
Do you know any particular reason for the PCG is affected by 6? Any particular reason? Because you know this, you can tune it.
Well, so for the blocking layer, there is they use the gap positions to the, and also this is also important how you are preparing like spray paralysis or spin coating method. And not actually so many people actually explain those kind of things too much. So from my knowledge, just I figure out like if the thickness is like too much, the resistance will be high, and this one can minimize my device performance.
Yeah, so the same slide, if I look at the 3D and the 5G curve,
Okay.
what I see is, you have a very high feed factor
Yep.
for 3D,
Yep.
but a very, poor current, which gets reversed in 5G.
Yep.
So what do you think, what's happening, and, what you can derive from these two curves to
Well-
understand, why your one layer, is giving you virtually lossless, transport out of the film, and if you just go up, you lose that property.
Yeah.
So, what do you think is happening, and have you considered?
Well,
Looking
this is
into
my
it.
questions. Just like Professor Jondal, he said, because this one is quite high, that's why we got high field factor, because field factor is dependent on the maximum voltage and maximum current from these things. And the things is for the 3 times we got high field factor, but 5 times we got less. So that's why we actually just wanted to compare these things. So that's why I use the voltage decay. The voltage decay is used like if the film thickness is low, optimum thickness, I'm not going to get very high thickness, but minimum thickness, there is very uniform and there is no pinhole. Only then this one can give very high fill factor. Because the fill factor is, I should say the fill factor is also depend on the series and shunt resistance. So, and series and shunt resistance is also quite relative to the device. So series and shunt resistance is also important for the compact layer. So, so this is quite reasonable for the compact layer thickness, resistance, and others. I also did like the, I checked the conductivity of a different layer. Actually, I didn't put it here, so in my slide. So. Yeah, you can just see the things like when I just increase the thickness of TL2 mesophores, compact layer, you can see the conductivity is decreased. So this is also one of the key points for the resistance.
Was there anything from 40 that was in between 3 and 5?
So for the 3 and 5, there is, I said, the device performance for 3 and 5 are quite close. That's why I use both of them, try again and again. Then I found like, if I use 3 times, I mean, this is the minimum thickness where I can go.
What thickness are we talking about, like?
60 nanometers.
And 5 GB?
5 is about 80 nanometers.
Okay. So there is a trick which you probably haven't considered. So what happens is optoelectronic device, right?
Mhm.
So if you increase the stack thickness
Mhm.
after a critical limit, then the field distribution in the device
Mhm.
changes drastically or increases drastically depending on the indices of those layers.
Mhm.
So and it really points very critically that there is this transition between 3T and 5T where you are moving away from let's say lossless regime to somewhat like a lossy regime.
Okay.
So if you pay attention on that one, you'll probably find a way to optimize your devices rather than swapping thicknesses beyond a certain level.
Well, this is of course a very important suggestions. As I mentioned, like I used spray pyrolysis method. So,
Yes.
so like
You don't
most
have
of
the precise control.
So the problem is like when we use the spray pyrolysis, it's just hand made. We are using hand pump at the beginning. So I developed these things to hand pump to the regulated pressure with the nitrogen. And then when I changed to this phenomena, and there is a very unique, I make some sort of holes in the spray positions. So there is like, it's mixed with the nitrogen and also mixed with the TiO2 solutions, and giving the films is quite different than normal using the hand pump system. So this is different. That's why I put in my future works that I want to use different environment to check the compact layer. Is there any kind of phenomena because of the spray process for the device performance?
Yes, important. Another thing I noticed that your approach is very good. You've done really a lot of work and made significant progress in optimizing your devices. But what strikes out is 2 things that you kept consistent. First thing is your substrate, which is FTO. Understand why you're using it.
Mm-hmm.
You should also compare what happens when you have ITO.
Mm-hmm.
And the other thing is you have always maintained this compact layer as an integral part of the device. But if you go back to your initial 3 different structures
Mm-hmm.
where you have PIN or NP, like NP or N-type. So you should also consider removing the compact TiO altogether and then using some other N-type layers that are capable of accepting electrons from the perovskite.
Yeah, that is also very true. And I said like last month there is one group work with the neighborhood blocking layer. They got really high device performance. But the main things for my project is mainly I will work with the whole transport materials and organic. So that's why I actually first 1 year I try to understand different parameters for making the device with high performance device. So so maybe in the future, beside my my current project, maybe I will consider.
Variation, yeah.
Mm.
One question,
Yeah.
My question is related to your compact layer.
Mm.
Typically depending on the compact layer, so of device performance. Okay, so I also don't quite understand why the GSC changed a lot from 3-layer deposition to 5-layer deposition, or 3-square deposition to 5-square deposition. And also which parameter that influence the GSC, like what should be the net of function and about charge transport and also charge collection? Which parameter do you think that is influenced?
Well, this is very true because we found like the JSC is very about 3 times the JSC is really very low. But if we go with the 5 times the JSC is quite high if you compare with the other the things. But mainly JSC should not be dependent on other parameter because we are using the same material, same time, so it should be almost the same. So I feel the problem is because the JSCs also depend on the charge transfer properties. So if the charge transfer properties has some problem, if the resistance high or other parameters, if there is any problem with the charge transportation, this one might be one of the reasons to have low
But
JSC with the.
why we first increase the thickness of film in the
Yeah,
JSC?
so there should be a trend, right? So there should be a trend like increasing these things. So there is one of the problem I found like for 2-step method to keep the JSC same always is not, I mean, it's not really very easy tough for 2-step method. Because 2-step method, this one have like deposition time and other parameters. There are so many parameters. So if there is something little bit change, maybe this is one of the reason. I mean, that's why I say like 1 step is more easier than 2-step method. That's why I actually then focus mostly to 1 step because 1 step can give me always almost constant JSC. There's no problem with this parameter.
Then when you compare iron oxide
Yeah.
and titanium dioxide, the efficiency is quite different.
Yes.
Big difference.
Yes.
Do you know what's the particular reason for this one? It's even the band alignment is quite close. Right?
Yeah.
Yeah, quite close.
Yeah, right.
Yeah.
This is very true. So the point is why I use the iron oxide. This concept actually came from the aluminum oxide. Aluminum oxide is an insulating material.
I think it's not important why you use iron oxide.
Okay.
The question is why the iron oxide, this device doesn't work well
Oh,
compared to
so
shell?
this one is just the one explanation I found from the photoluminescence decay. So
Oh,
you
so
can
this-
see, yeah. So you can see the lifetime here is
Lifetime.
50, yeah, 50 than the normal perovskite. So this is quite high.
What
So
does
it's-
it mean?
So it means it will stay on the iron oxide layer to not pass through the compact layer to the, our ATO or ITO. So that's why it's like a lot of electron loss or just isolated on the iron oxide film. So we are losing a lot of electrons. So that's why we are not able to collecting those things. So there is one of them, I feel.
Also from your MG band alignment,
Mm.
seems of it. The conduction band of iron oxide is actually
Yeah, so this is actually interesting point, like because it's just between these two things. So that's why I said like I also actually need to investigate more with the iron oxide because this is an interesting morphology and properties. If we can implement these things to high efficiency, then okay. Actually, I use the iron oxide for 2-step method also, and for the 2-step I got about like 2.5% of efficiency. That is higher than the 1-step method. So the thing is like, as I said, no one use, so still need to actually understand a lot about iron oxide.
Do you think you need to replace TiO2 if you want to use the iron oxide?
Yeah, this is one of the point. Maybe I need to use iron oxide blocking there instead of TiO2 blocking.
Yeah, you will find the reason you can
Yeah.
try to replace the best materials.
Yes.
And looking at your picture, like the energy level diagram that you've drawn, basically you should be drawing them to the correct like gap.
Yeah, it
Your
should be.
first guy looks like wider than
Yeah.
TI2,
Mm.
which is not the case because the gap for TI2 is wider than.
Yeah, because the iron
So
oxide is
to
middle of
design
this
this
thing.
thing when you put the numbers,
Mm.
because the schematic is fine, but the moment you have electron volt and those numbers,
Okay.
it should be justified.
Oh.
And probably you can see why your iron oxide is not working is you have a barrier from perovskite to TiO2. Not looking
Yeah.
at those. Don't look at this here. Look at this. That one.
Yeah.
So you have 4.9 and 4.2.
Yes.
So there's a big energy barrier there, and that's why you have almost like a capacitor kind of property where your charges are staying in rather than going out.
Yes.
So if you lower that one or take that one altogether, maybe you will have a better device. The other thing I noticed on slide 17 was you had this reproducibility data.
Yeah.
Where, so, okay, I can understand why the performance, falls, but then it is followed by, increase and
Yeah.
then a decrease. So what causes this increase? Have you ever paid any thoughts on that? Like,
Well, this one is used two-step method, so it's been.
no, it's the same device,
Yeah,
you're testing over days.
yeah.
On the first day, you have the best performance. On the third day, you have poor performance,
Mhm.
which increases on the fifth day. So what is causing
Yeah,
this trend?
so the point is, I'm saying the films remain like from the XRD, we show that films. So this one might be one of the reason the unreacted lead iodide in the samples causes the device performance fluctuation for long time.
No, but on the first day, it's not a problem.
Yeah, first day there is no problem, so.
But then it becomes
Falls
problem,
down,
and then
yeah.
it goes again.
Yeah, so that is why I need to actually understand the degradation mechanism. So
Yeah.
my guess, this is because of the degradation mechanism.
Yeah, you should understand
So,
because
so that's why I put like in the future, I need to understand the degradation mechanism, why this one is happening.
and on your outlook one or the future one, the last one, that'll be probably the last question from my side. So let's go get this one. So it looks like you have found the directions, but then you did not identify like what exactly you mean by mixing different carbon materials. So you haven't shown us like what material family you're going to use, because carbon materials like everything is carbonate, right?
Yep.
And the same thing goes on your, I think probably the way I see it is you rush through it, you did not like, put it enough attention.
Yeah.
Define
I
things
understand
and
what point.
finish your
Yes.
presentation. But then it also is an opportunity to show what exactly you're going to do next 2 years. So you should be very clear on what the material you're going to use. We know some examples that you had in the presentation. But then I didn't find anything about what is your protocol of stability, like how you will be comparing the stability of devices over time or in different environments, or what was the environment initially for your this data. So yeah, you should come up with a protocol where you say, okay, this is the literature standard and this is what I'm going to do with this variation or modification. So yeah, that would be helpful.
Yeah, this is a good suggestion. For the first one, like which kind of carbon I'm gonna use. So mainly, Perovskite is like this one have PNM type properties for the Perovskite layer. So some literature they say if they don't use any kind of whole transport material, this one can give device performance. So this is one of the key points. The second point is like people use PMMA. PMMA is a polymer which can make insulator, and it's not giving any kind of this one doesn't have any conductivity. So there is one work have done like they use also even
You
in our
can identify them as a semiconducting carbon materials or
Yeah, so-
insulators, that's what,
Yes, so actually my plan was like, because I was focusing too much on the device, I
Yes, we
mean,
can see from this
I
presentation.
receive. That's why the point is like I was a little bit far because the first point I thought that if I can know the different layer which can give me high performance with the existing materials, then it will be more easy for me if I implement any new materials there. Then I can compare both of them. Why the new material is not working? So for me, just I spent 1 year to understand the device performance to get a high efficient device. In the meantime, I read literature and also close look on different carbon materials which is used for the Perovskite layers. Actually, I didn't put those kind of materials here because this one is, if I put it will be more lengthy and more literature based. That's why I didn't. So the things is like I already finished this thing, so actually I'm going to use my first carbon maybe within this month or next month. And this kind of works actually have done in our group before. One of our postdoc did those bamboo type carbon material with the P3ST, and the paper is already published. So the concept is we have like different nanocarbon materials. Right now we have carbon nanotubes, yes. So this is the point actually we are going to implement those carbon materials in the process. So this is we just keep those things, didn't put it here because there are some like those things not published, don't want to share those things at this moment. Because the Perovskite is very, I mean, a lot of people are working. So the idea is like whatever. Even there are some ideas like last time I try to use that things like the mixing with the high reduced graphene oxide with the TiO2. When I was working these things in the early October, then I stopped to work with another things. Then I found a paper actually published on November. They use the high graphene oxide.
Yeah,
So the thing is like I thought these things October, I just did, but I didn't complete it. Then someone just published it. So that's why.
Because, everyone is trying to improve, so.
Yeah, so that's why.
For the P-type organic materials, it seems many P-type organic materials are unstable.
Yeah.
Unstable.
Yeah, so right now in our group, like one of our members is working with the nickel oxide, and also we have another plan to use like copper iodine or copper sulfate, those kind of materials. So this is just the initial thinking. We haven't actually, just nickel oxide is already used, but the other is not used, so we will use these things from my next year.
So there are four directions you are going to work in your field in the next 2 years. Which area are you going to focus?
Well, so mainly because I already tuned the device parameters and got reasonably high performance. So if I can keep the performance at that level or a little bit higher, then I think for the commercialization it will be enough. So that's why my focus will be mainly on the whole
I'm focused.
Yeah,
I'm focused rigidity.
Yeah.
Yeah, I focus on.
Yeah, so I will actually focus on the inorganic.
I understand the sex and that is more important than just making device make high performance.
You should consider doing some optical simulations, which is already difficult, because you already have got the ellipsometry data somewhere.
Yeah.
So it just needs pretty level code that runs, and that would be much more helpful.
Yes, yes.
Understanding what's really going on apart from the
Yeah.
Yes, any question from the audience, please? No question? This is the opportunity for you to
It'll
help
be nice, ask questions, yeah.
and also understand Perovskite business.
Yeah, I try to make it easy for everyone like to understand Perovskite, but I think because of the time limit, I will be too fast. Maybe some of the parties don't understand. Yeah.
I just want to know one.
Yeah, yeah.
Can you go to that slide where you're showing different website and their data?
Yep.
the value for the lead chloride, is it pure lead chloride or iodine mixed? CG and the second one, is it 2.2?
2.2. This is for the mix with, no, there is no lead chloride mix.
Ah, it's the pure lead.
Yeah.
Excellent. Yeah, it's interesting.
Okay.
So, the higher band gap, you should expect higher density.
Because of the band gap position, this can give like the voltage is related to the voltage.
Trade-off, you get a high voltage
Yes.
or low current.
Low current. So the main things in the Perovskite is like you have to trade either the JC, then you'll get high VOC. But if you can tune this in the middle, then high JC, high VOC, good film factor, then the device will rise. So that is why people like to use a lot of EPUDs, because it's very easy to change the band gap position. Yeah. Yeah.
You saw the three kind of structure of the perovskite,
Mm.
planar, mesoporous
Mm.
structure.
Mm.
So which one is better? You can compare the mesoporous and planar structure divide. Which one you can compare?
Yeah, okay, this is good. Because I didn't actually work with the inverse structure, I just mainly focus with the mesoporous and the planar. So the mesoporous is actually two-step method to make the device, and planar is one-step method. So in my work, like mainly I started with the two-step method, mesoporous. Then I also focus with the one-step method because I found like one-step can more easy to control the film thickness. That's why today I got the highest efficiency one-step method with the planar structure.
So now we compare to the, I remember when I read some science paper,
Mm.
maybe to divide the big difference in the Q factor of
Yeah. And also, because when you use the mesoporous layer, this one can help you to get the device stability also can be improved. So some of the planar structure is not only using the compact layer. I also use compact layer and also I use the mesoporous layer. But the deposition method is not two-step, just one-step method. I mean, I mix the solution and put the perovskite layer on the mesoporous layer. So I have also the structure. I mean, in this community, it's not here, but my device is also the same concept. It's two-step, but just minimize two-step to one-step. But I use mesoporous layer also. Because you see for the iron oxide device, so there is I show like 1.5 times. This one, this is the mesoporous layer.
I have a simple question.
Mm.
You said the penthouse
Mm.
affects the quality of the film and also the performance of the device very much.
Mm.
Can you try like deposit perovskite layer 2 times using the one-step method?
Mm.
Just 2 times.
Mm.
First you fabricate 1 layer of perovskite, and then maybe you do some heat treatment, and then use the second layer to block these pimples. Is that possible?
This is also a good idea because I also tried that one. I already tried that one, but the device performance was not good. There is one point you have to know, like if we can increase the different layer, but there is a diffusion length for different perovskite materials. So when we are increasing the layer thickness, it means the diffusion length will be also changed. So if we cannot tune those diffusion length and with the thickness, then the device will not get good performance.
What do you mean the diffusion is changed? What do you mean?
It's not. The point is like because the thickness of the film will increase.
But you can tune the concentration of the solution and make 2 thin layers by using another kind of 2
Yeah.
thickness.
Yeah. So the point is because I tried once in this method in my existence and it didn't give me good performance, then I actually didn't know how to read it. So I just busy. I will consider this thing for my future.
Yeah, the reason why it won't work is when you have your first layer and you want to process the next layer, this layer will be washed away.
Yeah, yeah,
So it
because
is
of
the
the
same solvent. So you dry it, you make it, and then you use it. So it's
What
approach.
about using like spray coating
Spray.
other than?
No, unless
spray
unless
coating?
you make a sequential like two solvents where one doesn't mix with the other, that approach will not work. So that's an entirely different. Like,
Thank you.
Any other question?
Otherwise, I want to ask you, have you checked about in the literature review for the open circuit voltage with the backside smooth, the roughness, the relation?
With the roughness?
Yeah. You're in different literature,
Uh,
you mean
no.
the SEM different morphology compares different efficiency, but in that table you didn't mention the open circuit voltage.
Well, in the literature, it's not that like specified things. But for here, I actually also didn't actually focus the things like if the roughness morphology has anything with the things, because the compact layer is we spray the things and it's very thin, so the morphology is almost same, but the roughness is different.
And not for the compact, I mean for the perovskite layer. You mentioned in the literature review part, you give also SEM for different
Yeah,
groups
yeah.
results.
Yeah.
Have you got some relation for the voltage with the morphology? Whether it's the drop with the lower voltage?
Perovskite layer actually, the roughness of perovskite actually didn't too much influence the voltage. So I actually didn't check it. I can think it out.
Okay, if no more questions, so we will close this seminar. And thank you for coming. And then the panel member will discuss